Look for A? Look for A? Wonder how fast something's happening. It can't just be an A. Wonder how fast something's happening.
So distance per time.
dAdt. I want to find dAdt.
It's the same as the last one, right?
I agree. It is remarkably similar, and it's actually better because you're going to use Pythagorean theorem instead of law of cosines. So find dAdt when what? When b is 5.
I mean 5.
That's right. When b is you got me saying. Ha ha! When b is 5. Okay. In notation, that's what you want to do. I'm telling you, if you can get down to notation and figure out what you want in terms of mathematical notation, it makes the problem a lot easier.
Oh, since we know 2 sides already, C is always going to be 13 ladders now.
We don't know the 2 sides.
B, we know at a certain point B is 5.
At a certain point, b is 5. That's right.
As soon as you put
Okay, fine.
So then C is always going to be 13 because the ladder is shrinking.
That's right.
We can just plug in and find what A is.
So now, you made a good point here. Since c is constant, you are allowed to plug it into this expression. A and b are changing this whole time, right? As the ladder moves this way, b gets longer and a gets shorter, correct? So a and b are changing the whole time. So this expression, a squared plus b squared equals c squared, these two are changing. This one is not. It's always 13 because the ladder is stuck. So you could write this as a squared plus b squared equals 169. Okay? So now when you take the derivative, it's going to be easier. It's going to be 0 on that side instead of what? Instead of 2c dc dt, which is worthless to you, right? Because you're going to be looking for dc dt in a second. You're not going to see it up on the board, right? So because that's a constant, you can fill it in to begin with, right? Like over here, we filled in the 45 degrees, right, to begin with. Okay. So now we take the derivative of both sides, and we're looking for dA dt. So if we apply dt to both sides, we will get 2a dA dt plus 2b dB dt equals 0. And again, if it had not been constant, you would get 2c dc dt. It's a very standard derivative expression to get in these types of problems because a lot of them have to do with Pythagorean theorem. But we can write the right-hand side as 0. All right, we just need to solve for dA dt now. No big deal. So dA dt, just subtract this and divide by that. So dA dt, once you make that subtraction and division, the 2's will cancel, and you will get negative b dB dt over a. Agreed?
Yeah. Yeah, because
Subtract this, divide by the 2a. And dA dt is by itself now. So what we want, dA dt, we need to find out what it is when b is 5. All right? So if b is 5, I can fill in b right here. What's dB dt?
0.5.
It's always 0.5, right? I can fill that in. It's always 0.5. All I will need to fill in now is the a. I don't have the a.
We can use Pythagorean theorem.
I can use Pythagorean theorem. I can plug it back into this and find out what a is. So the unknown a squared is going to be plus 25, right? Plus 5 squared equals the 13 squared. Look out, I'm falling over. Isn't that a 5, 12, 13 triangle? Is it? I think so. Right. 169 minus 25 is 144, which is 12, right? Well, 144 is not 12. The root of 144 is 12, right? All right, so you have a equals the root of 13 squared minus 5 squared. For those of you that like Pythagorean triples, this is a fundamental one, the old 5, 12, 13 triangle. Okay? Like the 3, 4, 5, you know what I'm talking about? All right, good deal. So that equals 1 up from 11, which is 12. And now we have all the components for this algebraic mess here. So we have negative 5 times 0.5 divided by 12. So 0.5 is really a half. So that means there'd be a 2 down here with the 12, so it's 5/24. This equals negative, wait a second, 5/24. So now what are the units?
Wait, what did you put in there?
Negative 5/24.
But what's
It's point,
that?
0.5 is 1/2.
Then what's that squiggly thing? Oh, that's from the previous thing?
What's the squig? Where's the squiggle?
It's at 12, I guess.
That 12?
Yeah.
Yeah.
Okay.
That's not supposed to be attached.
Okay.
A little bit of space there. Yeah, it's 12.
Isn't
That's
it,
feet per second. Because this is not an area, this is just a distance this time. It's not A for area, it's just that vertical distance versus time. So we would have feet per second. Okay? Good job. Now this one turned out to be negative, which makes sense. The thing is falling downwards. The usual construction is to fall downwards. What's that? As you go downwards, usually that's the way people set up problems, is that going downwards is negative. But if you had said, oh yeah, it would all work out.
So we could use it for any point that's falling down. So you said 0.8.
Oh, you're saying use this expression?
Yeah.
Yeah, you could have found it anywhere. You could know how fast it's falling down right when B is whatever you want. Just plug it all in. We just happen to want when it's 5 for whatever reason, and that's the magical number in this problem. When it's 5 feet away from the wall. So now you know how fast it's going to crush his head, right? -524s.
Wait.
That's what it's going to get him.